Let's do an easy problem today that's devoid of any context. Let's find the integral of x squared from 0 to 3. Okay, you know how to do this right away. Let's go ahead and do it right away with the fundamental theorem of calculus. Find an antiderivative of x squared. And you can say antiderivative too. X cubed over 3, right? Because you can always check it by differentiation. We're using the reverse of the power rule here. We're adding 1 to the exponent. The 2 becomes a 3. And dividing by that same number as long as we don't divide by 0, which is always going to be okay to do as long as that exponent is not -1. Check it by differentiation. You'd bring down the 3. 3 times 1/3 is 1. You'd also subtract 1 from that exponent. You would get 2. You would get x squared in the end. If this were an indefinite integral, you'd want to put the plus c there. That's got to be there for the gateway. The gateway is all about indefinite integrals. Plus c needs to be in part of the answer to every single question. But for definite integrals, you don't need the plus c, because if you put it there, I mean, it wouldn't hurt to put it there, but if you did, it would cancel when you do your subtraction, applying the fundamental theorem of calculus, FTC. You're evaluating this from 0 to 3, which means, this notation means, plug in the top number and subtract what you get when you plug in the bottom number. And so far, for all my examples to this point, we've been subtracting 0, but we won't always. And in fact, we'll do another example today where we will not subtract 0. So it is worth writing there for emphasis, even though it's 0. In the end, 3 cubed over 3 is 27 over 3 is 9. 9 minus 0 is 9. The exact answer is 9. If this were an applied problem and this were, say, a t squared, instead of x squared, t for time, and the output of t squared representing a velocity, so the velocity depends on time, in, say, meters per second, this integral would give you your displacement. Though with the t squared graph, it's always above the axis, it would always be a positive velocity. So displacement, change in position, would be the same as distance traveled. So it would be, if this were in meters per second, this would be in meters. So we know the answer right away, but we did see last Friday that sometimes the FTC, while it's still true, is not helpful. Right? It was the integral of cos of t squared last time. The answer involved Fresnel C, which you've never heard of before. Although maybe I talked about it in Calc 1 last fall. It's just a new function you've never heard of. There are hundreds, if not thousands, of new functions out there that you've never heard of before. Do I know them all? No, I don't. Okay. Not even very well, because I don't really study them. But they are out there. You can use integrals to define functions. That's part of the point of integrals, in fact, is to define new and possibly useful functions. To help us do integrals like that, though, we have to do numerical integration approximation. So we want to remind ourselves here in a simpler example how to do numerical integration. Let me talk about the general setting first. You've got a continuous function. This is for numerical integration here. Numerical integration. You've got a continuous function f on a closed interval from a to b. That's closed interval notation. This means all the numbers on a number line between a and b, including the endpoints. You pick a value for n, which is the number of subintervals that you're going to break this bigger interval into pieces. N subintervals, ultimately for the left and right hand rules, it'll be n rectangles that will approximate the area under the curve. to keep things simple, make all the rectangles have the same width. Actually, sometimes it's handy to use widths that are not constant, though that's pretty rare. So mostly we want them to be the same width, call it delta x, to be the length of the interval, which is b minus a, divided by the number of subintervals. So this will be the width or length of each subinterval. I could call it the base of each rectangle that I use. Here's a picture. Here's our interval from A to B. We're breaking it up into n pieces. There's the first piece. Here's the second piece right there. The third piece, fourth piece, etc. There's the last couple pieces. The next thing I'm about to show you is probably the trickiest thing. You let A have another name. Call it x sub 0 or x naught for short. Not x naught, but x naught. Not N-A-U-G-H-T. Naught kind of means 0, right? Nothing. X naught. Let that be A, the left endpoint. Let the next point right here be x1, then x2, then x3, then x4, etc. B is going to be x sub n. If there's n subintervals, that's got to be the case, because the first subinterval has a right endpoint x sub 1, second one x sub 2, third one x sub 3, the nth one has to be x sub n. Yes, in math we do say nth. That's the nth subinterval. The second to last is x sub n minus 1. The third to last is x sub n minus 2. And yeah, these are all the same length, delta x. Based on this setup, we can write down a formula for the general point x sub I, where I could be 0 or 1 or 2 or 3, etc. through n. Let's do it by pattern recognition. First, I'll put a question mark. X sub 1 is x sub 0 plus delta x. Or let's go write it in terms of A plus delta x. X sub 0 itself does equal A. X sub 2, look at the picture, is x1 plus delta x. But x1 can be replaced by A times delta x, A plus delta x. And then delta x plus delta x is 2 times delta x. X3 is x2 plus delta x, and then the x2 can be replaced by A plus 2 times delta x. 2 times delta x plus delta x is 3 times delta x. You see the pattern? In general, x sub I is going to be A plus I times delta x. I can be any number, 0, 1, 2, 3, etc., up through n. Does this work when I equals n? Does this equal b? Doesn't look like it does it? Well, that's because you haven't replaced delta x with what it equals and simplified. The n's divide out, then the a's cancel, and it does equal b in the end. Once you've got all this set up, then you are ready to write down formulas for what are called left-hand sums and right-hand sums. Left and right, they're really functions of n. Left of n and right of n. Let's write them first without summation notation, but then we do want to get used to using summation notation. For one thing, That'll make it a lot easier to program Mathematica. It's also something that you encounter in many textbooks is summation notation, sigma notation. It's something that people sort of like are a bit afraid of. You want to get used to them, and so you can deal with summation notation when you see it and make sense of it. With the left-hand rule, for each subinterval, we take the left endpoint and use that to determine the height of the approximating rectangle. We're trying to approximate the area under the curve. So we're using the heights of rectangles to make rectangles whose areas will approximate the area under the curve. For the very first subinterval, the left endpoint is x naught, x sub 0. That'll be f of x sub 0 will be the height of the approximating rectangle, and its base or width will be delta x. So that's the first term in the sum. It's the area of the first rectangle. Again, for the first subinterval, go to the left endpoint, go up to the graph, and then make a rectangle based on that height. It's got a base of delta x. The next rectangle, the second one, will be for the second interval. Its left endpoint is x1. Plug x1 into f to determine the height, multiplied by the base delta x. You get this. Keep doing that until you get to the last one. The last interval, the nth interval, the left endpoint is, it's a little hard to see here, x sub n minus 1. That's the left endpoint of the last interval here. Plug that into f to find the height. Multiply times the base again. This is the last term in the sum. All those delta x's are the same. So the delta x could be factored out. And when I do a numerical example, I will factor it out. But I think it's worth keeping here for the sake of two reasons in each term, to emphasize that each one of these terms that are being added is an area, a height times a base, area of a rectangle, and you're adding those all up. That's worth emphasizing. Let's wait for the summation notation. For the right-hand sum, you do the same kind of thing, except you use the right endpoint of each interval instead of the left endpoint. So the first interval, the right endpoint is x1. Second, it's x2, etc. The last one, the nth one, the right endpoint is xn. So we get a similar kind of summation, except we started with f of x1 instead of f of x0. And we end with f of xn instead of f of xn minus 1. All right, let's write these with summation notation now. Capital sigma. So it's also called sigma notation. The sigma means sum. It's not a coincidence that sigma starts with S, just like sum starts with S. What are we adding up? We are adding up products of the form f of something times delta x. What's the something? X sub 0, then x sub 1, then x sub 2, etc. In general, call it x sub I, where I starts at 0 and goes up to n minus 1. It's assumed here in this notation that I keeps going up by 1 unit at a time. First it's 0, then it's 1, then it's 2, then it's 3, etc. The last value I is n minus 1. The right-hand sum is very similar, except start I at 1 instead of 0 and go up to n instead of n minus 1. So a very similar kind of thing. Let's go ahead and do this for our example. For this integral where we know the answer is 9, let's see how good the answers are when, say, n equals 5, for example. And we also want to know about what are called errors in the approximations. And there's a very special way that I want you to compute errors. That is standard. So let's apply it with a equal to 0, b equal to 3, n equal to 5, and f of x is x squared. Let's just do a right-hand sum. Right-hand sum with n equal to 5. I've got to figure out delta x. Delta x is b minus a over n. So that'll be 3 minus 0 over 5, which is 3/5, or 0.6. So this also means x0, this is worth writing down, is 0, x1 is 0.6, x2 is 1.2, x3 is 1.8. I just keep going up by 0.6 every time. X4 is 2.4, and x5 is 3. For the right-hand sum, we use those numbers. We don't use the 0th number. We don't use x0. So I get f of 0.6 times 0.6 plus f of 1.2 times 0.6 plus f of 1.8 times 0.6 plus f of 2.4 times 0.6 plus f of 3 times 0.6. F of x equals x squared. Let me also factor out a 0.6. F of 0.6 is going to be 0.6 squared is 0.36. 1.2 squared is 1.44. I'm evaluating f at these different numbers here. I'm evaluating these inside the parentheses. 1.8 squared is 3.24. 2.4 squared is 5.76. And of course, 3 squared is 9. That gets multiplied by 0.6. I factored the 0.6 out. Add these up, 0.36 plus 1.44 plus 3.24 plus 5.76 plus 9, 19.8 times 0.6 is 11.88. So it gave us an answer that's too big, right? The real answer was 9. Why is it too big? It's not the concavity. In this case, it's the fact that it's increasing. The concavity affects whether the trapezoid rule is an overestimate or underestimate, but here the graph is increasing. The right-hand rule is going to give you areas that are too big. They're going to look about like this. The rectangles are going to be above the graph because the graph is increasing and we're using the right-hand endpoints. Left-hand rule would be too small. In fact, the left-hand rule with n equal to 5 would be the exact same summation, except we would start at f of 0 times 0.6 and end at f of 2.4 times 0.6. 0 squared is 0, so we would get 0 plus 0.36 plus 1.44 plus 3.24 plus 5.76. The 9 would not be there. In fact, the 19.8 would then go down by 9 to 10.8 because of the 0 here and the 9 not being there anymore. 10.8 times 0.6, 6.48. And yes, that's too small because the left-hand sum is giving you areas of rectangles that are below the graph because the graph is increasing. If the graph were decreasing, which one's bigger and which one's smaller would get flipped around. For a decreasing graph, the right-hand rule is too small and the left-hand rule is too big, the opposite of what happened here. And it makes the most logical sense to probably just try to average these. It's called the trapezoid rule, when you do that, average these two numbers, 11.88 plus 6.48 divided by 2. 11.88 plus 6.48 is 18.36. Divide by 2, you get 9.18. Pretty close. Why is it called the trapezoid rule? The reason is because it can be interpreted in terms of areas of trapezoids, which have the same base, but they have a slanted top instead of a horizontal top. Connecting points on the graph with straight lines. So I just drew some red lines there. They're not, it's not a curve, even though it looks like the blue curve. I meant for those to be line segments, straight lines that are tops of trapezoids. And the sum of the areas of those trapezoids, I only drew 3 of them, there would be 5 for this example, is your best approximation with this information to the area under the curve. Yeah, that's pretty close to 9. Later in chapter 7, we will be learning about 2 other rules called the midpoint rule and Simpson's rule. The midpoint rule is actually a better approximation than the trapezoid rule is. And it can still be interpreted in terms of trapezoids, it turns out, but it's trickier. It's where you take the midpoint of each interval instead of the left or right hand endpoints and use the midpoint to determine the height. Simpson's rule is then a weighted average of the midpoint and trapezoid. The trapezoid is an average of the left and right. Add them up and divide by 2. Simpson's rule takes the trapezoid and midpoint rule, which I have not written down the midpoint rule here, and does 2 times the midpoint rule plus the trapezoid rule and divides by 3, gives the midpoint rule twice the weight, because we'll see it's like twice as good. I do want you to know how to find errors in approximations. What I'm writing down is not really explicitly in chapters 5, 6, and the beginning of 7 in the way I'm going to write down. It's later in chapter 7. But I want you to know it now, including for the mini exam. We can write down, say, E sub L of n, E sub R of n, and E sub T of n. The E's stand for errors. Notice they're capital E's, they're not the number E. Although in Mathematica, the number E is a capital E. The L stands for left, the R stands for right, and the T stands for trapezoid. So in general, what are they? I always remember it as actual value minus approximate value, and that's really nice. And I never forget that because actual comes before approximate in alphabetical order. The actual value is the integral itself from a to b. And the approximate value is going to be the approximation you get from the left-hand rule in this first case. In the second case, it's going to be the approximation from the right-hand rule. And in the third case, it's going to be the approximation from the trapezoid rule. Now I'm writing the integrals in these formulas because that's what these errors are. But realize when you're trying to approximate the integrals, you're not going to know what the integrals are. You're not going to know what the exact value is, except in simple circumstances. So while these formulas are true, you have to approximate not only the integral, but you also have to approximate the errors. Actually, what these are most important for is coming up with what are called theoretical error bounds, which can be computed. They're theoretical and practical, you might say, because they can be computed. We will see examples of these, I think, at the end of chapter 7, but especially in chapter 10, I think it is, when we do the Taylor series stuff. We'll do similar kinds of things to approximate functions instead of integrals. So in the present example, for our example, EL of 5, N was 5. The actual value of the integral is 9. The approximation we got from the left-hand rule was too small. That was the 6.48. So the error is 2.52. The error for the right-hand rule is the actual value minus 11.88, negative 2.88. The error for the trapezoid rule was the actual value 9 minus the approximation 9.18, negative 0.18. And you do want to do it this way, actual minus approximate, and get positive errors when the approximation is too small and negative errors when the approximation is too big, which seems a little funny. Like, why would they do it that way? There's a good reason, but I'm not going into it right now. For the moment, it just helps you keep track. Positive error when the approximation is too small, negative error when the approximation is too big. Actual minus approximate. You would like these errors to be close to 0, like maybe that close to 0 or closer. These are pretty bad errors, you might say. That can be fixed by picking N to be bigger. Choose more rectangles, make them skinnier, and approximate the area under the curve better. But that would be a big pain to do by hand. So now we can turn to technology. You can certainly make little programs in your calculator to approximate these things. Of course, you also have the numerical integration feature on your calculator itself built in. But we do want to get good at being able to use Mathematica, for example, as something else you can do. So here's where you're going to want to take notes on Mathematica. And you do want to make a habit of using Mathematica to check your work, even when I don't tell you to use it. It is a good tool for checking your work when you know how to use it. It's also a good tool we'll see for helping you understand what's going on. First, define your function, x squared. Whenever you define a function in Mathematica, first of all, it needs a name, like f. Function inputs go inside square brackets, not parentheses. When you first define the function, the variable goes inside there with an underscore after it. That is essential. If you forget the underscore when you first define the function, it will not work right. Once you've defined the function, then don't use the underscore anymore. It'll work. Things will go bad if you do after that point. Only use it right at the beginning when you first define the function, as I'm doing now. Enter this by putting your cursor somewhere in this line and doing shift return. If you have a long keyboard, you can also just use the return at the far side of the keyboard, on the far right side. It is entered. I can change the function. I can change it to like x cubed, re-enter it, and I get a new function, x cubed. Or cosine of x. It gets updated. The memory gets updated, even though it's in the same spot. I can also clear the function. I can type clear f, and then nothing stored. But I want that function there, so I'm going to re-enter it, and now it's in there. Specify a and b. Say a is 0 and b is 3. Actually, I'm noticing that it's when I'm typing these now, they're coming out showing black. The variable x is green because it's a variable. If I clear a and b and then retype the same thing, you'll see that they're blue. But then I enter them, they turn black. Okay, it's sort of a way of seeing whether a quantity is a value stored in a variable or not, is whether it's blue or black. The semicolons officially just suppress output, but I kind of like to think of them as separating different equations, different lines of code, so to speak. What I'm about to do is optional, but I think it's handy. Define delta x as a function of n. Hey, where'd that triangle come from? That's Greek letter delta. I did escape, capital D, escape. Escape, capital D for capital delta. Escape makes a delta. Delta x, this is one quantity. Just like it's one quantity when we write it by hand. It's not delta times x, if you've ever been confused about that. Delta x is one quantity. It's b minus a over n, right? That's what I wrote by hand. But n is a variable, so I need a variable for this. B minus a over n. Notice the n is green. Enter all this. If you want to confirm delta x is in there, I could type this without an underscore, and it should return b minus a over n. 3 over n is what it equals. Yeah. B minus a is 3. Let me define a function for the left-hand rule. It also depends on n. By the way, you may also be noticing I'm doing colon equals for these functions. That's not necessary. A plain equals sign works, but I make a habit of doing colon equals for some other reasons I'm not going into. How do we get the summation in there? We need to use a palette, like the writing assistant here, which you can get to through the palette's menu. There's a basic math assistant, a classroom assistant, and a writing assistant. They're all pretty similar. I like the writing assistant slightly better. It's fairly big. You can make it small too. There is, if you got your cursor on the right spot, a summation button you can click right here. Click it. Boom. There's a summation. Type an I. Tab over to the next box. Type a 0. Tab up to the next box. Type an n minus 1. I just tab to get to those boxes. You also can, instead of tabbing, just click on the box. What am I typing here? F of xi times delta x. Yep. Delta x is delta x of n. Don't type just a delta x because I'm treating really delta x as a function name. Yes, it does represent a value when you plug in a value of n. Don't just type a plain old delta x, type delta x of n. But what goes in here? That was x sub I. What was our formula for x sub I? Yeah, right there. A plus I times delta x. That's what goes into F. A plus I times delta x of n. I've got functions within functions here. Notice square brackets around the n, but all this a plus I times delta x of n inside of F, the input for F. I can enter this. Let me put a semicolon here. And I can plug in the number 5, for example, with a decimal to get a numerical approximation to confirm what we found by hand with the calculator, that the left-hand sum is 6.48. Yep, there we go. Once this is all typed in, we want to do more. We want to do the right-hand rule and the trapezoid rule too. Oh, it's a bit quicker. Magic a copy and paste. Copy, paste. Change left to right. Change 0 to 1. Change n minus 1 to n. Done. Enter it. Notice it's in the same cell, by the way. Here, I didn't have to put it in the same cell, but I did, and it's not a big deal. These individual cells are where you type your code. They're separated. This is one cell here. This is another cell here. I can compute the left and right at the same time in the same cell by putting them inside curly braces like this. Again, the decimal point just gives numerical approximations. There we go, 11.88. Then I can average them. for the trapezoid. I also can program the trapezoid rule for an arbitrary value of n like this. Oops. Fraction button, left of n plus right of n over 2. Notice the underscore when defining trap, but no underscore on the right because I've already defined left and right. Compute also after doing that, trap of 5, 9.18. Question? That just gives a numerical approximation. If I did not put a decimal sign there, it gives me a fraction. Though I can find an approximation for that fraction in a quick way like that. Oh, so does this confirm that the answer is 9? It's certainly no proof of it. What if I did trapezoid rule with n equal to 100? It's really, really close to 9. Okay, what if I did trap with n equal to, say, 100 billion? 9. That's a lie. Okay. What do I mean by lie? It's really not exactly 9 yet. The left, right, and trapezoid rules are never going to give exactly 9. So how do we know the exact answer is 9? I mean, right? That's what we did first. That was the fundamental theorem of calculus. We got exactly 9. How do we know the true answer is exactly 9? I mean, how do we know it's not 9.0000000, maybe with a million zeros and then a 1? How do we know it's not that? But you might say it's just too simple of a situation, just x squared from 0 to 3. How could it be something weird like that? And that's probably a pretty convincing argument, though it's not a proof. What do we do instead? How about limit? Calculus is all based on limits. You can't get away from them, in theory at least. In practice, you can, right? We do those limits back in Calc 1 for derivatives, and then we say, hey, okay, we're tired of doing that. Let's use the power rule, product rule, quotient rule, chain rule, blah, 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 and avoid limits, and it's great. With integrals, we can avoid limits as well. Fundamental theorem of calculus, it's great. But it's based on limits. The theory has to account for limits. In this case, a limit of areas of rectangles as the number of rectangles gets larger and larger, goes to infinity, and the rectangles themselves get skinnier and skinnier. Delta x goes to 0. You never actually have infinitely many rectangles, but you can take a limit of, say, the area you get with the trapezoid rule as n goes to infinity and see if it's 9. It is. Wait, how did I make that arrow on that infinity? I made the arrow by doing minus sign greater than sign. It morphed into an arrow. I made the infinity by doing escape INF, escape. Also on the palette, there is an infinity button. Where is it? There it is right there. There's an infinity button you can use too. Does that work with just the trap? Does it work with left? Yeah. Does it work with right? Yeah. For any value of n, those things are not equal for any fixed value of n, but in the limit as n goes to infinity, you get the same limit. Wait, what are these things? How is Mathematica just approximating the integrals there? What are these things? Oh, there's the trapezoid. It's got a formula which can be simplified to something pretty simple, huh? And yeah, that's an expression as a function of n that definitely goes to 9 as n goes to infinity. Wow.